Okay, now all the gremlins are gone. We started this problem here, for some of you tuning in a little later. Maybe this sample is taken out of the blood. The results show we got 59% carbon, 26.2% oxygen, 7.70% nitrogen, and then there's hydrogen left. So your classmates had said, and that is correct, you're going to add these three numbers together and subtract from, of course, 100%. Okay? And it doesn't matter if you start doing that first, like we said, you're not wrong. You're going to have to do that at some point. But what we were saying before I finally saw that, okay, now we can record, one of the aspects you're going to have to get out of your head from this after this chapter moving forward, what do we see is the difference when we see that, when we see this, and if we see this, and we see this. Let's see here. Nope, that's not 35. It's 70.90. What do you remember from physical science do those all have in common? They're diatomic. So that's one of the things that happens moving forward when we start talking about reaction stoichiometry. You might be looking back and saying, well, I remember when we took this divided by 14.01 and 16. Yes, that is true because that's just composition stoichiometry where you're just dealing with one compound. We're not changing forms or anything to that nature. So it's one of those things to where sometimes that can be a tough transition, but like we said earlier this year, should you fall down, look to your left or look to your right. There's someone there to pick you up and keep pressing forward. Live for another day. Okay? So we see we got hydrogen in here, but we don't know how much, but we can calculate that though. And how would we go about calculating the amount of hydrogen? Okay, we add all them together, so 59 plus 26.2 plus 7.90, subtract 100, and that gives us what for hydrogen? 7.91?
That's 92.1 the whole thing, but it's 7.1.
7.10 grams of hydrogen. So now we're getting this set up. Our molar mass, our mole of hydrogen, 1.01 grams of hydrogen. So then, once we got this set up, we are well on our way to calculating this. Okay, so 59 divided by 12 gives us 4.91 moles of carbon. Okay, 26 divided by 26.2 divided by 16, 1.64. Yes. Yep. That's if it's zero digits. And it might come to that should we not get good numbers from this. But yes, I did say if we end up with something like if it says 0.003 and then there's other numbers behind here, okay, we want you to go to 3 non-zero digits. So yes, that is correct, but for our purposes, this should still work. I mean, it's not guaranteed, but it gives us a place to start. And what does that do for our nitrogen?
0.55.
Okay, so 0.55, and maybe we should go one more. 549. Okay.
549, but I read it to 5.
Okay, and that might still work. But since this is less than 1, like these aren't, these should work. But since this is less than 1, we're going to go out one more digit. And then for our hydrogen, 7.10 divided by 1.01 probably gives you pretty close to 7. 7.03 3. If 7.029, I think we're safe doing this. Now, remember what this is saying is that inside the bloodstream, we've got these elements. We've got carbon, we've got hydrogen. It doesn't matter which order you put them in, nitrogen and oxygen. But as we know, we can't say 5 moles of carbon, 1.5 moles of oxygen, half a mole of nitrogen, and then 7 moles of hydrogen. Once you get to this point, your final step is what? Divide by your smallest number. So which this is pretty simple. So if that leaves that at 1, we've got 1. And we divide this by 0.549, and we get, okay, so we'll try, so yeah, we would put this as 13. So 13 moles of hydrogen, okay? Dividing this by 0.549, and this one here, 0.549. And what do we get for carbon then? Okay. And then for oxygen, okay, so 3.50 moles of oxygen. You got 3? Okay. So 1.64. Okay, 1.64 divided by 0.549. You get 2.98, which is pretty close to 3. This is what you get, 2.98, which we could say that could be rounded up to 0. That rounds that up to 0. So therefore, 3 moles of oxygen. So all of these numbers came out nice and neat. So therefore, what happens is now we can start putting these in here. We've got 9 moles of carbon. We've got hydrogen was 13. Nitrogen's 1, and then oxygen came out to be 3. Okay, so then again, if this was a calculate the molecular formula, you would have to be given that, and then all of these numbers together, empirical formula mass, into a molecular formula mass. Okay. Takes a little bit of time to do these, but gives you a sense of, these are, my opinion, quite complex when you're getting numbers that are bigger than 10 or approaching 10. That makes that just a little more difficult. And again, it's our job to maybe raise the bar just a little bit, so then if whichever you encounter this in college, we can withstand that and say, I'm confident that, I have a pretty good grasp on this and know how to do this. And then hopefully it comes around to the point where people are asking you for help, okay? And I would think that could be quite common, okay? So that's why the hard work you're doing here at this level will help you in your next level. All right, front row. We're on the bus. Middle row. Middle row. Middle row. Middle row.
What are we doing?
Oh, okay, so answer for the middle row. There's nobody there. Okay, so back row. All right, so with that, again, we have one more day to go over these, naming compounds, problems like this, okay, molar mass problems, percent composition problems, and hydrates. All right, so it's a good thing we're not going through a hydrate problem because they're your dehydrating things. We want you to be hydrated for tonight. See, that's why we did that problem yesterday. We didn't want to do dehydration today so that we're all hydrated. See, that's just thinking ahead. That's not thinking behind, that's just remembering things. Okay, so with that, we will conclude for today. We'll catch up to you next time.